All right, hello. Today we'll be looking at problem 2.20 from Griffiths. And this is a great problem because it goes through a lot of good concepts with the gradient of V for the voltage and for find the electric field with the cross product the curl. Anyways, one of these electric fields given here, this one is an impossible electrostatic field, and our job is to figure out which one that is. So to start this problem, we want to think of the fact that for electrostatic fields, our curl here, so our gradient del operator across the electrostatic field should equal 0. If it does not, it's not an electrostatic field. So let's start with A here. So if we calculate that, we have our constant K out here, and then we have our vector. And remember, the way to calculate our curl is to simply take the determinant. So I'm going to have this x hat, y hat, z hat times the partial derivative, or just partial derivative with respect to x, respect to y, respect to z. Then we have xy, 2yz, 3xz. Okay, so what does that equal? If we do it, we get k times, so now we're taking our actual determinant here. So remember, we're kind of just, for the x1, we're getting this times this minus this times this. So that is d over dy 3xc minus d over dz. And this is our x hat component. Y hat. And then I think this is just be minus. Okay, so let's just simplify some stuff really quickly. First off, when you have a partial derivative with respect to a variable that's not there in your equation, like here, it's just 0. So this is 0. This is 0 since there's no z in our function. And this is 0. So we only have these guys. Okay. So let's calculate that. So it's equal to k times negative 2y x hat plus 3 cy hat, and then minus xz hat. This is not equal to 0. So this is not an electrostatic field. It's impossible. All right? So we can definitely say that's not an electrostatic field. Let's take a look at the other one, though, just because it is good to check both, even though we obviously know the answer. I'll just put this down here for now. So we have E equals don't want that. Okay. Now let's take our determinant. Whew. Anyways, now let's do a little bit of simplification again. Looks like there is no x component in this, so we can make that 0. No z component in this function, so we can make that 0. Can we do that anywhere else? Nope. So now we have, this is equal to k times, let's see, what is the partial derivative with respect to x of 2xy? That is, oh, no, let's do the first one here, the exact thing. Partial derivative with respect to y of 2yz is 2z. And then minus, this thing goes to 0. But this is 2z. Remember, we already had 0 for y hat. And then take the partial derivative with respect to x for this c component. That's, oops. That is 2y. This thing goes to 0. And then minus 2y. Oh, wow. Look at that. We see that these cancel out. So it's 0 x hat plus 0 y hat plus, you guessed it, 0 z hat, which all equals 0. So our cross product is equal to 0. Therefore, this is an electrostatic, can't spell, field. Okay, well, we did that, but we want to check our answer by computing. Let's see, what do we do here it's asking us to check our answer by computing. Right, okay, I see. Boy, this is a dedicated problem. So, I'm just gonna copy this here, go here. All right, I remember why this was such a good problem. So we want to find the potential of this guy. Well, yeah, so we want to start by finding the potential. So find potential. So remember that phi is equal to the negative integral E dot dl. So maybe a good thing to do would be to draw this out into 3 sections, I guess to say. So we have a z component, we have a y component, we have an x component, and our function has basically 3 paths it takes in our different coordinate directions. So we'll say in our first path, we're just going x hat direction. Then we're going in the y hat direction. And then we're going up here in the z hat direction, getting to our final point here. Okay, so let's solve this integral here by starting with the dot product. So we have E dot dl is equal to so when we say dl, remember dl is equal to x hat dx plus y hat dy plus z hat dz. So we're taking the dot product of that with our function. So we're just adding a dx to our x hat component, dy to our y hat component, and dz to our z hat component. So our equation comes out as ky squared dx plus 2xy plus z squared dy, and this is going to run out, so I'm going to pull it down, plus 2yz dz. Okay, so we want to integrate over these different paths. So what we want to do here is, say for path 1, we'll look at our components. We see that our dy change in y is equal to 0. We see that our dz change in z is also equal to 0 because, we're just going across the x hat direction. So you can say that our E dot dl is equal to just ky squared dx. And then we can also see that when we take the derivative, with respect to x, since we're doing dx, is equal to 0. Okay. Path 2. Path 2 is across the y hat direction, so we say that dx is equal to 0 and dz is equal to 0. So our E dot dl is equal to this part derived with respect to y. So that will give us, we can get rid of this z component. So it'll just be k 2x y dy plus 0 for our z component. So I guess we're not actually deriving with respect to y yet, but since there was no y component in the other part, we just know that will be 0 when we integrate, because there's nothing to integrate over. So let's actually go to our integral here. And we see the integral from 0 to y naught. So this is y naught is equal to k times 2x naught. Because we're out to some x naught here. Times the integral from 0 to y of y dy is equal to k2x naught times 1/2 yo squared is equal to k xo yo squared. Oh, it's a long problem. Path 3, we say that our dx is equal to 0, and we say that our dy is equal to 0. So then our E dot dl is equal to k times 2yz dz. Okay, so we can just say that's equal to k 2y naught, just because we can plug in our y naught that we have up here, and then z dz. So then when we integrate, we'll be integrating from 0 to z naught. Z naught's where we'll be going up in z. V dot dl is equal to k 2yo. I'm just pulling out the constant. So integral from 0 to z naught of z dz, and that is equal to k yo. This is just 1/2 zo squared, so the 2 and the 1/2 cancel out, so it's kyo zo squared. So, we said all the way back up here, like 10 years ago, that, we're taking the integral of E dot dl. So we add up all of our dl components. So our potential is equal to, and also remember there's a negative there, and I guess I forgot to mention that, under each of these paths, when we were doing these integrals, like this integral, we didn't do any integral for path 1, but we were taking that integral, or the potential, so the r is kind of like our line. So We already took care of the integral as well, so we just have negative k xo yo squared plus k yo zo squared, right? And we can just pull out the k. Almost there. So now we can finally do what the problem was asking originally, because we have the potential. So check your answer by computing the gradient of v, because remember, E is equal to the negative gradient of v. So when we take the negative gradient of v as equal to our k, and I just took care of the negative there, two negatives cancel out. So k times, so we're taking the gradient, so it's d over dx of xy squared plus yz squared. Remember, that's just coming from here. X hat plus d over dy of xy squared plus yz squared, y hat plus d over dz of xy squared plus yz squared. Don't want that. Z hat. That is the ugliest z. Okay. So lots of derivatives there, but it's not too bad. Let's see. So you have gradient v is equal to k times, let's do the first one. This just goes to 0 because there's no x component. So that is just equal to y squared x hat plus 2xy, let's see, plus z squared y hat. And then for the last part, this doesn't have any z component, but this does. So it's plus 2yz z hat. Okay, and then this is equal to our electric field. So let's go all the way back up. We saw that our electric field was this earlier, and it actually matches. Awesome. And since that matches, we have checked our answer. We see that the electric field is equal to the gradient of v. So there you go. That is the proof. And this is our verification that this is an electrostatic field, and this cannot be an electrostatic field. Thanks for watching.